Welcome to this video in where I'll be talking about training convolutional neural networks, and I'll also be focusing on the CIFAR-10 dataset and the building pipelines and the preprocessing pipelines. So first of all, this section of the code, this is used to suppress CUDA warnings whenever you are importing TensorFlow on a CPU computer, that is a computer with no GPU. So to suppress CUDA warnings for TensorFlow, use this code here. So then I import the libraries that I'll be using for our training, our tutorial today. So this CNN model is the model architecture here. So I have edited the architecture that I had built last time because that architecture was extracting the images to the point that we were getting negative image dimensions, which was bringing an error. So I had to reduce the properties and the layers of this architecture in order to accommodate training of the CIFAR dataset. So then if you make changes to this file here, use the imp library to reload the importation. Since if you use this one, it will import the cached version. So in order to import the original version which has new changes, use the imp library. So we're going to use the Civility Data Set, which is the Civility Data Set. Essentially, it's composed of 60,000 images of size 32 by 32, and its color images, meaning it's RGB channels, and it's composed of 10 different channels, with each class having 6,000 images. So the classes that are in the CIFAR dataset are the ones I highlighted. So there are 10, so meaning our model will be having output of 10, and the input will be 32 by 32 by 3 since it's RGB. So I want to extract a subset just for this tutorial, but you can use the whole dataset. So then I initialize the class names for the CIFAR dataset. So let us visualize a sample of the images. So when we visualize a sample of the images, we see that they are really low resolution, and so the model training cannot achieve a very high accuracy on this dataset. So it's really mostly used to train CNN architectures, because this is where you can practice the techniques of model tuning in order to make the model better at classification, since this data is of really low resolution. So we visualize the data. So before we train the model on the CIFAR dataset, we have to do normalization in order to ensure that every pixel of the image has a similar data distribution, which helps in convergence of the way of the network while training. So there are 3 ways we can normalize. We can normalize between 0 and 1, we can normalize between -1 and 1, and we can normalize with mean of 0 and standard deviation of 1. So let us start with the first one. So for the first one, we just divide the images by 255, both for the testing and training, in order to normalize them to the range of 0 to 1. And then we now initialize our model, and then when we can see, now view the summary of our model, and can see that we will be training 60 million parameters. And if you also notice that most of the trainable parameters are in the dense layers of the convolutional neural network. So that means the layers before, especially for convolution and max pooling and also batch normalization, they are mostly used only for feature extraction, though they also have trainable parameters. So after viewing the model summary, we can compile the model in order to tell the model the optimizer that we'll be using, the loss that we'll be using, and the metrics that we'll be using. So if you if you train our model here, it will train on the dataset and learn the patterns in the dataset that will lead maybe to a specific class. So here we will specify epochs of 1, but can specify maybe 100, meaning 100 iterations over the dataset as the model trains, and then we specify batch size of 16. So the model will take a batch size of 16 of the images and the labels and train, and then go to the next batch size until it finishes the whole dataset. Then the validation split is the argument that helps in taking a subset of the train images and labels for validation. So that is now how we can do training using preprocessing, where we do preprocessing before the model training. But generally, it's a good practice to develop models that take raw data as input, as opposed to models that take already processed data, as we have done above. So the reason being that if your model expects preprocessed data, anytime you export your model to use it elsewhere, e.g. in a web browser or in a mobile app, you'll need to implement the same exact preprocessing pipeline, which can be a bit tricky to do, especially if you want to maybe use it in mobile. You convert to TensorFlow Lite version. You will find that it will be very tedious to do. In fact, you can get maybe it's not really been implemented in terms of the preprocessing functions that you can use. So it's always best to do the preprocessing within the model. So that's what we are going to cover in the section that follows. So if for now in this case, if we want to normalize in the range 0 to 1, we can now create a preprocessing layer for normalizing in the range of 0 to 1, or if we want to normalize in the range -1 to 1. So basically, for normalizing in the range -1 to 1, we'll have to set the weights on our data. So when we set the weights, we create a temporary pipeline that will use to set the weights. So here I set the weights, then I specify the mean and the variance. Then after setting the mean of the variance, now I set the weights to the model. Now when I get the weights, we see that we have for the mean we have 3 values, since we are training on RGB images, and for the variance we also have a set of 3 values that we will be using for normalization. So that is for the range of -1 to 1. And then when we normalize with the mean of 0 and standard deviation of 1, so this is the default normalization for the normalization layer, where the adapt first takes the data, it pre-computes the mean and the standard deviation, and then after pre-computing the mean and the standard deviation, we now set those mean and the standard, the pre-computed values, to be the weights of the mean and the standard deviation. So now when we want to build now the model that will accommodate the preprocessing within the model, we stack both the layers that we want to deal with and the model. So in this case, I do the scaling, then I also attach the model. So I stack the two. Then so this larger model will do the preprocessing within the model training, or even during inference, the preprocessing will be done within it. So there's no need to pass. So in this case, when we are now instantiating our data set, there will be no need to do our normalization before, because we know that the model does the preprocessing within the model pipeline. So if we want to maybe now to, instead of using the range normalization the range 0 to 1, if you want to use normalization in the range -1 to 1, you just change it here to be -1 to 1, then If I want to use maybe the one with the mean of 0 and standard deviation 1, I'll use this specific format. So then now after running here, sorry, the error is saying expected dimension 4 found 3. Sorry, but that's normalization, mean and standard deviation. So scaling layer. So when I run it, we see that we can do the preprocessing within the model. So I can also try this one. You can also see the so about this one, mean std. I'll talk about the error in the next later on. So now after doing the scaling together with the model, after stacking them, now I can compile it and then train it. So apart from doing the preprocessing within the model, we can also do the data augmentations. So what augmentations does is to introduce sample diversity by applying random yet realistic transformations to the training images. This helps expose the image to the model to different aspects of the training data while slowing down overfitting. So we can do the augmentations layer. Then now in this case, now we stack all the three together. So now if we stack all the three together, then I compile it, then I can do the training with the compiled version. Yeah, so I think in this case scenario, what I had to do, I had to specify the input to the pipeline, so 32 by 32 by 3. So now if I run it, it will be okay, but because it had no input pipeline, it was now producing the error. So the issue is we have to specify the input to the model. Yeah, so that was the issue. Now here we can do the augmentations layer. We stack it with the preprocessing layer and the model. Then after that we compile it and we train it. So in the above sections, we have been doing the training with the numpy dataset, but it is recommended to use tf.data.Dataset object because of the reasons that we can read in this section here. So to convert the data to tf.data.Dataset object, we can use two functions. We can use the from tensor slices, and we can also use the from generator. So the from tensor slices, it adds the whole dataset to the computational graph. So this one is especially inefficient for data which is memory intensive. So when we run our data here, it will convert our data to the tf.dataset object. So now that if we view the type of our data, we see that it's now of tf.data.Dataset object, And then now, instead of now passing x train and y train as two different arguments, now pass it as one. And then for the test dataset, we also pass it as one. So remember that if you are training the model, rerun the option to the one for loading the dataset again, because remember that earlier on we had normalized, and now since we are using the model version which does the normalizing within the model, there's no need to normalize the image. So you just take the raw images and load it. So in this case, now after loading it as it is, we convert it to tf.data.Dataset object, we batch it, and then we train it. So another part, apart from using the from tensor slices which adds the whole dataset to the computational graph, we can also use the from generator which adds the data in batches to the computational graph. So for this function here, it takes the image and dataset and image and labels, and it creates a generator and it adds it to the from generator, where we now create our dataset from which we return it with the batch that we require. So in this case, this code here is the same as this one. The only reason is this one is deprecated, but if you uncomment this one the first one can still work. So the generator will yield the image and label, where now you specify the data type of the image as float32, specify the data type of the label as int32, that is labels 0 to 9. Then we specify the shape of the image as 32 by 32 by 3, and we specify the shape of the label as 1. So in this case, we have two tuples. This one specifies the shapes of the images and the labels, and then this one specifies the data type of the images and the labels. Then the first argument is the generator function. So this one is deprecated, so now you can use this one, where it uses the output signature as the argument together with the generator function. Then you return the batch size, and now this is how you you create the tf.data.Dataset object from the numpy data. We specify now with batch size of 32, and also for the test we specify batch size of 32. Now after doing that, after it will import both of the two, and then after doing that, now we can do our model training. So after doing our model training, to evaluate with a batch dataset, you just pass it this way. Though if we are using the one with numpy data, you just say x test, you must pass two arguments to our model during evaluation. And we see that now we are using, for the model, the last part, we are using the activation softmax, which we say that normalizes the probability labels in the range 0 to 1, and also makes the labels to have a summation of 1. And so we can also do the model.predict of a single image, of which we know that if we take a sample image, we can get a single image. But now if we want to predict it, or if we want to predict the single image, what you must do is you must create a batch dimension for the single image in order for the sample image to have a batch of 1. So this is necessary whenever you want to maybe do a prediction of a single image. So in this case, if we see the shape of the single image, we see that it has a batch of 1. So after training, you can predict the labels, which will be vectors of 10. Then now to get the specific correct probability, you use the tf.math.argmax, then you pass prediction, then it will extract the correct probability. So if you find some issues with the argmax function, you can do a flattening. You can do a flattening, which essentially is to reshape the prediction. So tf.reshape, this one will flatten the prediction, and then you use tf.math.argmax, or you can just use numpy function, which is argmax, and then you pass the predictions. So this is how you can do an inference of a single image. If you want to do an inference of a batch, let's say like the whole test data set, there's no need to do the tf.expand dimensions, because as we can see, the X test is already in rank 4, so there's no need to do expansion. So that is all on training CNNs and building and preprocessing pipelines. So thank you for watching.